should be able to explain this. Yeah. Okay, so we were talking about the connection between SO3 and SU2. What we did last day quickly was this. We talked about the group manifold of SO3. This has a fancy name, but what we understood it to be is a solid ball of radius pi. If this had been all, then SO3 would have been a rather simple thing, but it's not, because with antipodal points on the surface identified to each other. So each pair of antipodal points on the surface really counts for a single rotation or a single point in the group manifold of SO3. SU2, on the other hand, has a group manifold of S3. Okay, well, of is not really the right word to put here, but anyway, group manifold S3, and this, although S3 of course is a bit more difficult to visualize than S2, which is the one we have experience in, it's sort of easy to understand that S3 has the same kind of properties as S2. In particular, it's simply connected. Whereas SO3 was doubly connected in the sense that you had loops in SO3 which could not be contracted to points, but which, when traversed twice, could always be contracted down to points. Okay. However, why are we talking about these two groups in the same breath? Basically because of the result that we talked about, that SO3 and SU2 are homomorphic. There's a homomorphism map, SU2 and SO3. This map is a homomorphism. It's an onto map which also preserves the group multiplication structure. Now, while it's mostly enough to know that a homomorphism exists, in this case the homomorphism actually is simple enough to construct and is actually important enough for practical applications, especially in quantum mechanics. So, by the way, do you know what this map is? The explicit map which connects SU2 to SO3? Yes. Yeah, quickly. Do you know this? The explicit map, which given an SU2 matrix will give you an SO3 matrix, or given a transformation in this two-dimensional complex vector space, will give you a rotation, corresponding rotation. Any idea what the map really is? Yes? If you don't know this, okay, then we can go ahead and talk about it. If you already know about this, there's no point.
There is actually a connection with the rotations of spinors.
Well, there is a connection with the rotation of spinors, but that's indirect. Okay, that's something which comes in because the spinors essentially transform in a particular way under rotation of coordinates. And that's true. However, after all, an SU2 matrix will be a matrix which will act on a 2 by 1 column vector. So a spinor being a 2 by 1 complex column vector essentially transforms according to that. However, how do you exactly connect the matrices of SU2 to the matrices of SO3? That's what I was asking. I'm pretty sure you already know this. You have seen this somewhere or the other, but may not know that this is the connection that we are talking about. So it's one of those cases where you may know the answer, but you may not identify the answer at this stage. So let me just give you a hint. Does this ring a bell? This quantity, what is this? where R, of course, is a vector in R3. And sigma, of course, as a sigma vector, of course, is sigma 1, sigma 2, sigma 3. That's just a shorthand for this quantity, sigma 1 x plus sigma 2 y plus sigma 3 z. So does this ring a bell? Did you study
This
anything
is
to do with this?
this is a Hermitian matrix sigma dot r.
Yeah, it's not just
So
Hermitian. Okay, let's just write this out. This is z minus z, of course, because of the sigma 3, and then x minus iy, x plus iy. So since x, y, z are real numbers, as you rightly said, this is a Hermitian matrix. But only Hermitian? Is there something else you can say about this?
this traceless Hermitian matrix.
Okay, this is a traceless Hermitian matrix. And
Mm,
okay, fine. So this is traceless and Hermitian. Not only that, any traceless Hermitian matrix that you can think about can be put in this form, because if it's traceless, because it's Hermitian, the diagonal elements have to be real. Because it's traceless, I should be able to write the two elements like this, a3 and minus a3. And the other off diagonal element, the off diagonal element, if I write this as a1 plus ia2, this one has to be its conjugate. So it has to be a1 minus ia2, where a1 and a2 are real numbers. Which means that any traceless Hermitian matrix can be written down in this particular form. So sigma dot r is a particular traceless Hermitian matrix, a dot sigma, where a is, or rather any traceless Hermitian matrix is of the form a dot sigma, where a is some three-dimensional vector. Okay, but what else can you say about the properties of this 2 by 2 matrix? It's traceless
If
Hermitian, I agree. What else?
if we conjugate it with any to unitary matrix, it will again remain a traceless Hermitian matrix.
True. But even before that, let's take a look at a property for this. If you take any such matrix of the form that sigma dot a, the trace, of course, is 0. And the determinant, how much is it? It's just minus a vector length squared, right? Minus a3 square, minus a1 square, minus a2 square. So because of this rather special form for the determinant, this actually sort of is crying out for what you said. But what you need to do is take this matrix sigma dot r and hit it with a matrix U on the left, a matrix U inverse on the right. This is a similar transformation. Now, just if you did a similar transformation, then the trace would stay the same. The trace would be 0, and determinant would also stay the same, right? But it would usually not be Hermitian, right? Trace is the same, determinant is the same, but the Hermitianity is lost in general. However, you can keep this Hermitian by insisting that if U belongs to U2, that is the set of unitary 2 by 2 matrices, then U inverse, the same as U dagger. So this is a similar transformation, but it's also a unitary transformation in particular. And what happens then? You do a unitary transformation. This thing, U sigma dot r U dagger, if you took this and found this adjoint, you'll of course get U dagger's dagger, sigma dot r's dagger, U dagger, which is of course the same as U sigma dot r U dagger, because sigma dot r is Hermitian. So this is Hermitian. So we started with a matrix sigma dot r, which is traceless Hermitian, and its determinant is minus the length squared of the vector r. And you did a unitary transformation on that. The result will be traceless, will be Hermitian, and will have a determinant which is the same, right? So because it's the resulting thing, because U sigma dot r U dagger is traceless Hermitian, then always write that, as we just saw, any traceless Hermitian matrix can be written down as sigma dot some vector. And the connection between R and R prime would be R prime's length squared has to be the same as R length squared. So what you can easily see is that uh, this transformation on R, which is induced by the transformation by this unitary transformation on sigma dot R, is actually going to be an orthogonal transformation, something which leaves the length of the vector unchanged. Okay? So everybody is with me so far?
Yes.
Okay, so the next question, how do we know that this is a rotation on R? So basically, first of all, you can easily see that this connection, okay, if you wrote it out explicitly, say you wrote out the matrix U explicitly, you could easily see that this connection between R and R prime would be a linear one, right? You replace, or you don't even have to write it out explicitly, you just replace R by, say, alpha R. You can easily see that the number alpha will just go out, so you will end up with R prime, which is alpha R prime. You replace R by R1 plus R2, you will get R1 prime plus R2 prime. All that is straightforward. So this is linear transformation definitely, and so it can be written down in the form of a 3 by 3 matrix acting on the column vector xyz. That's straightforward. And this 3 by 3 matrix must be such that the transformation it induces leaves the length unchanged, so has to be an orthogonal transformation. So at least we know one thing, that if we use this to write down R prime equal to capital RR, then capital R at least should obey, this. That is, it has to be an orthogonal 3 by 3 matrix. However, there are quite a lot of gaps in this point. So right now what we have is a connection between a SU2 matrix U and a 3 by 3 orthogonal matrix. Sorry, we don't even have an SU2 matrix as yet. We have an U2 matrix U, and we have a connection between the U2 matrix and this matrix R, which is a 3 by 3 orthogonal matrix. So we need to specialize this a bit further. First of all, instead of any arbitrary U2 matrix, we want this matrix U to belong to SU2, and we want to also say that R must belong to SO3. That's only the first step in proving that this is a homomorphism. So first of all, what about this U? And there you can easily see one thing. Any 2 by 2 matrix U, or any unitary matrix, unitary 2 by 2 matrix, so well, you can always write that is everybody convinced about that? And can anybody tell me what this alpha quantity is? How do you find the alpha? Given a unitary matrix 2 by 2, how do you find this alpha? Such that it is I alpha times U tilde is U and U tilde is SU2.
You will take the determinant of symmetry.
Okay, so you will take the determinant of U. And one thing that you know for sure, determinant of U must be a complex number with modulus 1. Right? That follows from the unitarity. U dagger, U is identity. Take the determinant of both sides, det U dagger is the same as det U's conjugate. So det U multiplied by det U's conjugate is 1. So det U has to be a pure phase. Now that that is done, how is alpha, this e to the I alpha related to det U? Yes?
It will be exactly equal to the determinant of U. Because
Anybody?
U tilde has one determinant.
Yeah. So what is it? So now, anybody else with a anybody else with a difference of opinion? That it is the what we have heard right now from is that it is the I alpha is a determinant of U. Is that correct? Hmm? Everybody agrees that the I alpha is determinant of U.
Sir, e to the power 2I alpha will be the determinant of U.
Exactly. Because if you take the determinant of U, you will not get the I alpha times determinant of U tilde. You will get the I alpha whole squared. That's the determinant of U tilde. You must remember that when you multiply a matrix by a number, the determinant of the matrix gets multiplied by the nth power of that number, where n is the order of the matrix. So, the I alpha is actually the square root of the determinant of U. Okay? And why am I bothered about this U tilde thing? Simply because you can easily see that if you, instead of U, you wrote down the I alpha U tilde, and this will become U tilde dagger the minus I alpha. And the I alpha and the minus I alpha are just numbers, they will cancel each other out. So U and U tilde will end up producing exactly the same transformation on R. What that means is there are infinitely many unitary 2x2 matrices. Just start with any given SU2 matrix U tilde and multiplied by any phase factor that you want. You get infinitely many 2x2 matrices and 2x2 unitary matrices, which will give you the same transformation capital R. So since you want to get the relationship between these two groups as tight as possible, let's not work with U2. U2 has way too many matrices mapping onto the same R. So if you just use the SU2 matrix, that of course gets rid of this into the I alpha thing. But there's only one catch, which you can see simply in several ways, but one of them is just to look at how we got the alpha in the first place. We got the alpha by saying that the I alpha is square root of the determinant of U. But determinant of U has two square roots, right? Which one should we take? And in the complex plane, by the way, there is no reason why you should take the positive square root, because there's something special about the positive square root. You actually should take either one. Both ways you end up with a unitary matrix, which has determinant 1. The U tilde becomes a SU2 matrix. And the other way of looking at it, this is even if we restrict ourselves to U tilde to just SU2, U tilde and minus U tilde will of course give you rise. They are both SU2 matrices, and they will both give rise to exactly the same transformation. So by going over from U2 to SU2, what we have done is we have actually cut down a lot on the ambiguity of this transformation, on this many to oneness of this transformation. We're still 2 to 1. It's not infinity to 1 as it was before, but now it's 2 to 1. There are two SU2 matrices which gives rise to the same R. But I'm still waiting for this. How do we know that this R, which is an orthogonal transformation, is actually a rotation? How do we know it's SO3? Can anybody tell me that? Then, of course, start with a particular SU2 matrix, explicitly find the matrix R, and calculate its determinant. Or can actually start with an arbitrary SU2 matrix, carry out this transformation, find out the matrix R explicitly, and find out the determinant, and you will come out to be 1. That's one direct way of proving this result, that it is really an SO3 matrix. But can anybody give me a better argument? Yes? Okay, a hint. We were talking about the group manifold of SU2, right? Which was S3. How did we get that? We got that by saying any SU2 matrix has to be of this form. With alpha mod square. So the identity element, which is of course identity of SU2 is also this, corresponds to a particular point. So if alpha and beta are really expressible as x, y, u, v, that is alpha is x plus iy and beta is u plus iv, then the identity corresponds to the point 1, 0, 0, 0, right? So, okay, I hope you will pardon me for drawing or even attempting to draw a 2D sphere, S2, to represent the S3, which I, of course, can't draw the S3. The North Pole, or the analog to the North Pole here, 1, 0, 0, 0, is the identity element. Any other SU2 element corresponds to a point somewhere here. Now exploit the topology that we talked about, that SU2 is simply connected, or rather S3 is simply connected. So what can you do? You can actually draw a curve that join you from the identity to this any point on S3, which means any SU2 matrix. Now, as you travel on this curve, what's going to happen? What will happen to the SU2 matrix as you move from here to here? Here, of course, the SU2 matrix is the identity. When you get here, what is whatever SU2 matrix you're aiming at, say some alpha beta, alpha minus beta star, alpha star. But what happens as you move along this? That's very simple. The matrix changes, right? So it evolves from the identity matrix to whatever final matrix you're aiming at. Whatever SU2 matrix you're talking about right now. But notice that you are actually able to do this by going in a simple straight path all the way from here to here. What that means is you can traverse that path as slowly as you want. So at any given stage, the SU2 matrix that you get at the next step is very, very close to the SU2 matrix that you had in the previous step. In other words, you can slowly change the SU2 matrix or continuously change the SU2 matrix from the identity here to whatever matrix you are aiming at finally. So as, of course, the SU2 matrix changes, so does the matrix R corresponding to this transformation. Right? You started with utility equal to identity, so that, of course, gave rise to the identity transformation. Sigma dot R was exactly equal to sigma dot R prime. R prime was equal to R. So the identity matrix for capital R there. And as you slowly move along this curve, what's going to happen? The SU2 matrix is going to slowly change. As a result, the corresponding matrix R is going to slowly change until you end up with whatever R you have for this final SU2 matrix. So my question is, what can you say about the determinant of capital R from this argument? What? Yes?
It will just be one, right?
Why does it have to be one?
Because you're using R sigma dot
Okay,
R
R
U
is a matrix.
sigma dot R U inverse.
What?
Sorry. So that relation U tilde sigma dot R
Yeah, so we had this
U
relation.
tilde inverse. Hmm. Sigma dot R for U tilde mod of S square plus mod of S square equal to 1.
Yeah, I'm not sure whether I can hear you properly, but I guess what you're saying is okay. Maybe I need to. My system is free.
Hello.
Okay, I am still audible. I'm talking of U as a SU2 matrix right now. This gives me sigma dot R prime. And as I said, this means R prime will be some 3 by 3 matrix acting on R. And that will
Sir,
depend on
your
the matrix.
presentation can be seen.
Oh, my presentation has been. Can't be seen? Are you sure? Okay. My presentation stopped as a result. Okay. Can you see it now?
Yes, sir, we can see it now.
So this was what we were aiming at, right? This U, right now we are going to drop the tilde. This U is a member of SU2. And what we have said is for every U, there's a corresponding R, which you can find out. In fact, you can find out an explicit formula for this. And that's pretty easy. Uh, uh, well, any ideas how you would do that? Find out an explicit formula? Yes. Let me just give you a hint. You have this rather important property. Okay, forget the trace for the timing. Just you have an important property for sigma A, sigma B. Anybody remember what that is?
It's delta AB plus I times epsilon ABC delta C.
Sigma C. Yeah.
Mhm.
As
Actually,
I
if we
times.
consider the inner product induced by trace,
Yeah.
that
So
is,
basically, if you just take the trace, which is of course the inner product introduced by the trace. By the way, that's twice delta AB. This is real delta AB times the identity, 2 by 2 identity. And this sigma is traceless, so you end up with 2 delta AB. So all you have to do is multiply both sides by a sigma, any one of the sigmas, take the trace, and that gives you the corresponding x prime, right? And that should be able to give you a very nice simple formula for capital R elements, the Rij's, in terms of the U elements. Of course, there will be 2 U factors for every R coming from the U and the U tilde U dagger here. But what is important is this connection between R and U, which you can find out explicitly, but it's sort of obvious even without an explicit formula, is a continuous connection, right? If you change U slightly, R should change only very slightly. But if you change U slightly, R changes slightly, so does determinant of R. Okay? So all you can say is when you move on this S3 from the identity to whatever point you are going to, ultimately, whatever SU2 matrix you're going to, if you go slowly enough, at every given stage, what's going to, or anyway, you don't have to go slowly enough. You just go along this, you're continuously going from identity to this point. And so what happens is that rotation the matrix R changes continuously from the identity matrix, 3 by 3 identity matrix corresponding to this identity SU2 element to whatever final R you have. So fine. So all that tells you is the determinant of R can change continuously in the process. Why are you saying that this means the determinant of R is 1?
It doesn't make sense anymore. It's probably it should. Hmm.
What doesn't make sense anymore? Your argument or my argument?
No, my argument that the matrix is changing once you're
Yeah,
going
everything is
from
changing once you're
the
starting with that. It
identity.
has to, right? Because if you stayed at the identity forever, then this would be rather useless. Then this will still be a map from
Yes.
SO2 to SO3, but it will only give you the identity map. It doesn't give you that. It gives you different rotations for different values of the matrix U tilde.
We actually have the intermediate value theorem, which says that if determinant can take both the value 1 and -1, it should then take the values in between them.
True.
So, but
What's
we
the problem
know
with that? First of all, why 1 and -1? Why are you so worried about those two? I think even before you start talking about the intermediate value theorem, which is a nice thing to talk about, you should clarify why you said 1 and -1 in the first place. Where did the -1 come from?
because we proved that for U of two matrices, the corresponding matrices of O3 can only have 1 and -1 determinant, because
Yeah,
we already proved it's orthogonal.
right. That's the important point. The point is we know that for a given U, you must have a R which is orthogonal, right? Because the length of R and the length of R prime are the same. And if you have an orthogonal matrix, then the only two possible values of the determinant are +1 and -1. After that, once you've got there, then you can try talking about this intermediate value theorem and make it more formal. But it's easy to say that if you have only two choices, 1 and -1, then the only way you can continuously change is not change at all, right? Because you started with 1, because for SU2 matrix identity, you definitely had 1. They had the identity matrix for R, which had determinant 1. Throughout the process, the determinant can only change continuously, but since there are only two allowed values, it cannot jump from one value to the other. It has to stay at +1. So the real part of the argument is that there are only two possible values of R for det R. There are infinitely many possible values for the matrix R, but only two possible values for the determinant of R. And that is precisely why you start at 1, you stay at 1. So determinant does not change at all, it goes through as 1 throughout. So R belongs to SO3. So this is a map from SU2 to SO3. Because the map which maps U maps it to our matrix R. Sorry. Somehow I keep on confusing the matrix R with the real number symbol. It is just a standard 3 by 3 matrix. So this map is a map from SU2 to SO3. That much we have established. SU2 by choice, because we cut down our domain from all unitary matrices to just unimodular matrices, simply to make the many to oneness of the map a lot less. We have not been able to get rid of it, still 2 to 1, but at least it's not infinity to 1. So what else do we need to prove at this stage? What have we proven so far, actually? All we have proven is that for every SU2 matrix, you have a corresponding R, right? Which is a SO3 matrix. But is that what we wanted to prove in the first place? We wanted to prove a connection between the two groups, right? We wanted to prove, first of all, it's a homomorphism. Okay? So how do we know this is a homomorphism? For that, what you need to do is show that if you were to use the product of two SU2 matrices, here at least one advantage is we are actually using the defining representation for both the groups here. The utility that we are using, or which we are using, is actually an SU2 matrix. And the R which we are using is actually an SO3 matrix. So it's not something which mimics the group, it's just the group itself. So here, if you start by doing this, say you start with sigma dot R, use U1 to go to sigma dot R prime, then use U2 to go to sigma dot R double prime. So what do you get? You get sigma dot R double prime is U2 sigma dot R U1 U2 inverse or U2 dagger. And that's U2 U1 sigma dot R U1 dagger U2 dagger, which is of course U2 U1 dagger. And what this shows is well, if you this R double prime is actually R2 R1 R, right? Where R1 is what is it? The R1 is basically the map which is induced by U1, and R2 is the map which is induced by R2. In other words, U2 U1 maps to R2 R1. So this map between U to R actually preserves the group multiplication rule, or at least respects the group multiplication rule. So what you have is a homomorphism. By the way, our definition of homomorphism had an additional point. It was also that this map should be onto. But that is not something which every group theorist insists on. But it makes our life a lot easier if we assume homomorphisms to be onto as well, which makes statement of the other theorems involving homomorphisms much easier. So that's one more thing that you have to prove, that this map is actually onto. What that means is, given any rotation, you should be able to find out a corresponding SU2 matrix. So I will let you worry about that last part. How do you know that what we have proven problem so far is, given any SU2 matrix, you can get a rotation. Okay, and that this map between SU2 matrices and rotations actually obeys the group or respects the group multiplication rule in SU2 and SO3 respectively. So far so good. What I'm asking you to prove is, given any rotation in SO3, any rotation matrix whatsoever, you will be able to find a corresponding SU2 matrix. And in fact, you don't even have to explicitly find this out. You can actually argue this out just by using arguments along the lines that we have already used so far. Okay, so I will let you worry about that, how to figure this one out. Okay. So that essentially ends up proving that SO3 and SU2 are homomorphic to each other. They're not isomorphic, of course. It's not an isomorphism. It's a 2-to-1 map. And the kernel to the kernel of this isomorphism, then we call this map phi, the map which gives you U, which maps U to R. If we call this the map phi, then kernel of phi, what is that? Can anybody tell me what that is? Kernel,
minus
remember,
identity and plus identity.
which identity?
U of 2 identity. I mean 2 into 2 identity.
2 by 2 identity. So I2 and minus I2. Okay, these two are definitely in the kernel. Are you sure that these are the only two? That actually takes a bit of proving, by the way. We have been saying that the map is 2-to-1, but you should realize that we did not really prove that. All we proved that it's at least 2-to-1. U and minus U does obviously give you the same result. Proving that they are the only two matrices which give you the same result, that's not really that obvious. It takes a bit of work. Okay. All I'm trying to do is point out to you that certain things which are often stated quickly, and when you state them quickly and go through it, especially to a physicist's mind, these questions don't really arise. Do we really know that it's 2 to 1? We can see it's at least 2 to 1. Do we really know whether it's an onto map? All these questions really should be addressed properly if you're going to do this in any sort of rigorous fashion. Okay? You are right about this answer, but I will ask you to worry about why this is correct. Okay, this is of course isomorphic to the group Z2, right? Any two-element group is of course isomorphic to the group Z2, and which is why you will often see this statement. So this is one of the most famous quotient groups or factor groups in all of mathematical physics. SU2 quotiented out by Z2 is SO3. This, of course, is the second isomorphism theorem at work. If you have a homomorphism between two groups, just take the kernel of the homomorphism, factor out the original group, the domain group. With that, you get something which is isomorphic to the range group. I hope everybody is clear about this. I didn't prove certain results. I didn't prove it's onto. I didn't prove it's really 2 to 1. So I will ask you to worry about the proofs of that. It's pretty straightforward. These are not difficult. All I'm doing is trying to point out that these things should really be proven. They should not be taken at face value just because somebody said or some books said they must be. You have to work these things out. Okay? So any questions before we move on to our next topic? None. Okay, so can anybody suggest one more thing? Given the fact that we can find this connection, rather nice connection between a 2 by 2 bunch of complex matrices and SO3, well, can we do the same thing for SO4? Or perhaps what is more interesting to us right now is not SO4, but this is of course very interesting to all phases, right? SO3 comma 1, which is what?
Gives us the Lorentz group.
Lorentz? Okay, this is the Lorentz group, or this is isomorphic to the set of all proper orthogonal Lorentz transformations. But well, this is what we call SO3 1. Fine, because it keeps the 3 comma 1, of course, is because it keeps t square minus x square minus y square minus z square invariant. So, well, SO3 comma 1, of course, for that you need a 4-element column vector on which this matrix is going to work. With sigma matrices, we only have 3, right? We have only 3 sigma matrices. But we actually can write down sigma mu x mu, right? Or if you prefer the formal way of upstairs downstairs indices, where sigma lower mu is nothing but you throw in a sigma 0, which is the identity matrix. If you do that, what is this 2 by 2 matrix coming out to be? It's going to be simply t plus z right? So why are we interested in this matrix? What's special about this matrix? Think along the same lines as sigma dot r. What is the same? What is different?
It has the it has non-zero trace, but it's Hermitian.
Okay, let's start with what is okay. It is Hermitian, so this is one good thing. Hermitian, not traceless. The trace actually is twice t. Okay, and then
its determinant is the 4-dimensional Minkowski norm of x mu.
the sigma mu x mu is t squared minus R vector square, which is the thing which should be invariant under a Lorentz transformation. So just like we sort of figured out that doing a similar transformation on sigma dot R would give you a Hermitian traceless matrix, so you can write it as sigma dot R prime. But that was really not our main point. Main point was, if you did this, what you will do is it will also leave the determinant unchanged, so it will leave the length unchanged, right? Here, we have this nice sigma mu to x mu, or I will just call it sigma dot x from now on. This 4-dimensional analog to sigma dot R, okay, is Hermitian. It is a determinant which is a nice physical quantity. So if I do a similar transformation on this, okay, and of course I should really do a unitary transformation on this, not just a similar transformation, because I want to keep it Hermitian. And then I will end up with a Hermitian matrix which has the same determinant. So shouldn't that be a Lorentz transformation? If I started with sigma dot, I did just the same thing. I started with sigma dot x, do a u dagger, I get sigma dot x prime. This is Hermitian. Same determinant. So shouldn't this be a Lorentz transformation? Yes or no? In other words, have we really ended up showing that SU2 and SO31 also has a homomorphism?
Sir, can you repeat your question? I lost connection.
Okay, the point is sigma dot x is a Hermitian 2x2 matrix with determinant t square minus r square. If I do a unitary transformation on that, and I can, just as before, keep u confined to SU2, then u sigma dot x u dagger will be traceless, will be Hermitian, will have the same determinant. So will that be a Lorentz transformation on the connection between x and x prime? The x prime will be some L acting on x, some 4x4 matrix acting on the column vector x, which really is t, x, y, z. So will this L be a Lorentz transformation? Of course, I skipped a step, which was Hermitian, any Hermitian matrix. By the way, this is the sigma dot x of this kind, sigma 0 x0 plus sigma 1 x1 plus sigma 2 x2 plus sigma 3 x3, is a generic form for any 2x2 Hermitian matrix. Every 2x2 Hermitian matrix can be written down like this. That is sort of easy to see, right? The off-diagonal elements have to be complex conjugates of each other, and any pair of complex conjugate numbers can be written down like this. And the diagonal elements have to be real, and any pair of real numbers can be written down as a plus b and a minus b. So there's any arbitrary combination of the form sigma dot x is of this form, or anything which is any Hermitian matrix can be written down like this. So I should be able to write this result as sigma dot x prime. That's what I already assumed. And x prime, this sigma dot x prime is because it's Hermitian. And since the determinant is the same, it's a Lorentz transformation. So you were saying something about rotations. What?
The question that you asked is, if you use U as an SU2, so will that still give us a Lorentz transformation? So if we use SU2, then it's essentially taking the rotation part of the Lorentz transformation and keeping the boosts to no boost.
Why?
So
how are you so sure there are no boosts?
Because you have used U from SU2, and SU2 map onto SO3. So
yeah, but
these are just rotation.
Okay, you're right, but apparently we have just proved that SO3 and SO31 are homomorphic. What you are saying is fine, that we have already shown that SU2 maps onto SO3. But how do we know that this doesn't map onto a boost? That's actually very simple. You can just look at this and tell me that this is not a boost. Why is that? This is a Lorentz transformation, no doubt about that. But this is just the rotation and not a boost. Correct, as you said. But how do you know that this is not a boost? This can never give me a boost.
We did something. So I'll just look
It's
at
very, very simple. Very simple. It's
It's
staring you in the
even
face.
fixing the R squared also.
What? Sorry, could you just
I
repeat that?
mean, this conjugation also, I mean, this conjugation fixes the vector R square value.
Yeah, but it's much easier to look
It,
at it from another point of view, not just ask why are you looking at R square. It's much easier. In the one thing that I kept on saying, although I did, that's the problem of overthinking the thing. I was trying very hard not to talk about the trace. Okay, but since it was at the back of my mind, I kept on saying the same trace and so on. It of course gives you the same trace, but what is the trace? It's a unitary transformation, which is a similarity transformation. And similarity transformation not only leaves determinants unchanged, it also leaves trace unchanged. What is the trace of this matrix?
2t.
2t. That means
T is unchanged.
do any similarity transformation, time will not change. So it's a Lorentz transformation which keeps time fixed, which of course means it is a rotation. Of course, it could have meant also a reflection, but we have already seen that that can't happen, right? It has to only give you the determinant one possibilities. So, unfortunately, this apparently at least does not work. That is, sigma dot x, going that to sigma dot x prime. Remember what we did was hit it with a u and a u dagger. And since you hit it with a u dagger, you were getting a Hermitian matrix. And every Hermitian matrix can be written down in the form sigma dot x prime. So you get an x prime from an x with the same determinant, and that automatically ended up giving me the invariant correct, which would mean that this is a Lorentz transformation. But unfortunately, it also gives you the trace the same, which means time doesn't change. So this does give me a Lorentz transformation. It simply doesn't give me all of it. So fine, it just gives me the rotations, as has been said quite often. But this is the explicit proof of that you can't get the boost. But can anybody suggest how you would modify this a bit to be able to get all Lorentz transformations? Hint: to write sigma dot x after doing something like this as sigma dot x prime, the one thing that you really need to do is keep one property of the matrix sigma dot x intact. Which property is that? If you want to start at sigma dot x,
determinant.
First of all, let's not worry about the invariant length. First of all, can every matrix be written down as sigma dot x prime? If you give me any 2 by 2 matrix, can I write that as sigma dot x prime with real x's? Yes or no?
Only Hermitian.
Only the matrix is Hermitian can be written down as sigma dot x prime, right? Is that okay? So Hermitianity is the first property that you need to preserve. Okay? So a similarity transformation will not do in general. What you need is something which keeps a Hermitian matrix Hermitian, number one. Number two, and this is important, you don't really want the transformation, that is all the transformations to be similar, because similarity transformation not only keeps the determinant the same, it also keeps the trace the same, and keeping the trace the same will not work. It will only give you rotations. So what can you do? What can you do here so that, suppose I did this transformation where L is some 2 by 2 matrix. Will this transformation leave, the resulting matrix Hermitian? Yes or no? Yes, it will. No, it won't.
Yes, because
Yeah, what's your answer?
if you take dagger, then L dagger becomes L, and L becomes L
And
dagger,
sigma
and
dot
then
x is already
sigma
Hermitian,
dot
right?
x.
So this thing is Hermitian, where L is arbitrary. At this stage, L is arbitrary 2 by 2, right? No restrictions whatsoever. Okay? L sigma dot x L dagger is Hermitian, so can be written down as sigma dot x prime. Of course, the trouble is if you start with an arbitrary 2 by 2 matrix, then you have this problem that you have lost this invariance of the determinant. How can you keep the determinant invariant? That's what you want, right? If this is to represent a Lorentz transformation, you want x prime and x to have the same Minkowski norm, which would mean that the determinant of the matrix should not change in the process. So how do you achieve that? You wanted Hermitianity, fine. You can do that with any 2 by 2 matrix. But with any 2 by 2 matrix, the determinant will not stay the same. So what do you want to achieve? Want to force on L to ensure that the determinant stays the same.
Unit.
Sorry?
I mean, determinant of L and determinant of L dagger should cancel, I guess.
Great. Determinant of L and determinant of L dagger should cancel. Right. But that
So L must be unitary.
that would work.
I mean, L dagger.
Then L should be
L dagger equal to L inverse.
But if that is the case, then L is back to unitary, right?
Yeah.
And that means it doesn't work. So think. You're in the right direction, but you're overthinking. That's the problem.
Just absolute square of determinant of L should be 1.
So det L mod square, this should be 1. That's all you really need, right? Is everybody clear about that? Because if you take the determinant of this side, what happens? You don't really need a unitary transformation. Remember, determinants multiply. So you get det L, det this, det L dagger. And all you really need is det L times det L dagger is 1. Your original answer was correct. But you don't need, the only way to get that is not to insist that the matrix L be unitary. Is that okay? For a unitary matrix, of course, det L and det L dagger will cancel. But you don't need that. All you want is det L should be some pure phase. That's it. If det L is a pure phase, det L dagger is a complex conjugate, which is of course 1 by that for a pure phase, and they will just cancel out. That's it. You don't need anything else. Okay? But now comes this issue that if det L is some number, the same argument as before, you can always write L as it is a I alpha L tilde, and just by choosing alpha properly, all you can ensure is that L tilde is 1. And notice, L and L tilde will induce exactly the same transformation, right? If you put in e to the I alpha L tilde, you get e to the I alpha L tilde here. You get L tilde dagger e to the minus I alpha here. And these complex numbers just cancel each other out, right? So once again, this is an infinity to 1 map, but you can make it a lot narrower or a lot tighter just by insisting that instead of taking any 2 by 2 matrix whose determinant is a pure phase, you will just take a 2 by 2 matrix whose determinant is 1. As simple as that. Don't have to insist on SU2. Of course, if you insist on SU2, you're back to rotations. What you're really looking at is a homomorphism. That this is a homomorphism is pretty straightforward to prove, the same argument as before. So SO3 1 and the group on this side, the group which maps onto SO31 by this homomorphism. What is that group? The name of the group is? Quickly. Anybody? Set of all
SL2C.
SL2C. Set of all 2 by 2 complex matrices which have determinant 1. That's it. Any 2 by 2 complex matrix with determinant 1 will work. In fact, you need to go outside. Of course, SU2 happens to be a subgroup of this. But you have to go beyond SU2 in order to be able to get the boost. Okay? Is this clear? Yes? No? Any confusion? So what we have here is a map which essentially says SL2C is a cover of SO31 the same way as SU2 was related to SO3. And by the way, you all, at least some of you do know this, right? Anybody has worked in supersymmetry? Yes or no? Nobody yet.
Sir, I haven't worked, but the groups are independent.
Yeah, but so the spinners, how do they transform? They transform by 2 by 2 matrices with determinant 1. That's when you talk of general Lorentz boosts, Lorentz transformations.
Yes.
And that's why you have all these kind of dotted, undotted, defined kinds of spinners.
Yes.
Right? Because all these are, because now that you're talking of SL2C and not SU2, the daggers and the original ones are actually different representations. The complex conjugate representation is different from the, that's why you have a dotted spinner, you have an undotted spinner and things of that kind. But that's really all due to this particular connection, that Lorentz transformations are basically homomorphic to the SL2, the group SL2C. Okay, so anybody who has done any supersymmetry would be deeply into using this without perhaps knowing that you're using this. That's a different thing altogether. Okay. Now, having said that, let me just. Okay, what else do I have to talk about here? Do I really have anything left to talk about this before we can go on to the whole thing? Let's see. I was thinking about something which has just slipped my mind right now. Anyway, the point is, at least we can see that there is a deep connection between the fact, okay, and this is the reason why the generators of SO31 basically also are isomorphic to, but usually, unlike the SO3, SO2 case, it's actually the generators of SO31 which are better known perhaps than the generators of SL2C, which is why, although we are actually using generators of SL2C for the algebra, we don't really call them that. We call them boost generators and rotation generators. But we will come to that later perhaps. Okay. So this is basically what we had to talk about for these two very special groups. We could talk a lot. In fact, we should have talked a lot about the representations of the rotation group. But I'm assuming that you know all of that, right? Yes? Is that a fair assumption to make? That you're all familiar with representations of the rotation group?
Sir, you asked us to watch the quantum mechanics videos that you have uploaded. I have watched it halfway, but I haven't finished.
Okay, but if you take a look at that, you will, if you have not done this formally before, you take a look at that, you will essentially see the representation theory for the rotation group out there, although there I did not explicitly use the language of representation theory so much. But everything that we studied, or everything that we need to study, is already there. Okay, including direct product representations, reducing a direct product representation to to reducible to its irreducible representations and all that. Okay, so that's all there. Although when we talk about Clebsch-Gordon coefficients and or the Clebsch-Gordon expansion, we don't really use the language of reducible and irreducible representations, but you should be able to read between the lines there. Okay, the next day what we are going to do is we are going to start formally with Lie algebras. Of course, formally I should have started with Lie groups and talked about the connection between Lie groups and Lie algebras and gone on from there to talk about Lie algebras proper. However, we don't really have much time, and since Lie algebras are what you're going to use more often than not. By the way, don't assume at all that Lie groups are not really used in physics. Lie algebras are only. I'm not saying that at all. There are plenty of very important applications of Lie groups in physics, in the Lie group avatar, not in the algebra version. But frankly, the algebras are more common and more often used. So at least because we don't have a lot of time, we will continue with the Lie algebras in the next class. But let me just quickly give you a hint as to why Lie algebras are useful, although I'm sure you already know that. All we were saying is, suppose you have a continuous group. What does it mean? It essentially means that you have a bunch of parameters, say A, which maps say A1, A2 up to AR, let's say, which maps to a group element. So every group element G essentially has a bunch of parameters associated with it. And when you say it's a continuous group, what you are implying is that there's a continuous relationship between the parameters in this smaller dimensional space and the group elements. So, of course, for this to make rigorous sense, you need to talk about a topology on the group manifold and stuff like that, because without that you can't talk about continuity. But since most of the time we will talk about small fluctuations from the identity and so on, we will take those issues for granted. A full rigorous theory would require you to talk about the topology of the group manifold, talk about how continuity is imposed and so on. For the time being, we are not going to go into that right now. But the important thing is, if you compose two elements of this group, what you must get is an element of the group. It should be something you can express in terms of R parameters again. And what is important is each of these parameters Ci should be functions of all the A's and all the B's, right? So there should be R different functions, one for C1, C2, C3, all the way up to CR. And you get F1, F2, F3, or R functions. Or, as you all know, you can always say it's really not R functions, a single function which maps onto the R dimensional space. And this function F, or the vectorized version of the function F, all the R functions together, this should be continuous. This is what defines a continuous group really for us. That is, it's not only enough for the group elements to be parametrized continuously. What you demand is that when you compose group elements, okay, the parameters, of course, get composed among each other, and this composition rule should be continuous. This function Fi can be pretty complicated. If you just think about two rotations, rotations can be parameterized by three parameters. What three parameters could be? Could be two parameters for the axis, one parameter for the angle, or could be the three components of this theta length vector that we talked about. Could be the Euler angles. Could be just three rotations about the three axes. Whatever. But you definitely should know by now that if you compose two such rotations to each other, you get a rotation. And that the parameters of the composed rotation may be a very complicated function of the original bunch of three parameters each, right? The only case where you get a simple correction is when the rotation is through about the same axis, when of course the parameters just add. In other cases, the composition rule is way more complicated. Okay? But what is important is that we insist that the rule is continuous, and not only that, the inverse here will also have to be a group element, has to be parametrized, and what we insist is AI bar, that is the ith component of the parameters for the inverse, that should be a function of the original parameters, of course, and all the phi i's, or when you put them together as a vector, this also has to be continuous. So this is how you really define a continuous group. And notice that now that we are talking in terms of parameters only, things are much simpler because the parameters are really some member of capital R to the R, right? So what is continuity in that space is much easier to talk about. This is for the continuous group. Lie groups, what are they? They are basically an extension of this, where we essentially replace continuity by smoothness. That is to say, once again you have R parameters, and when you compose two group elements, you do get a group element. And what you're insisting on now is that these functions Fi are actually differentiable. Really, strictly speaking, what you insist on is not only that they're differentiable, that they're analytic. Both the composition function and these functions, AI bars. Okay, the inverse, the function which gives you the inverse parameter, the parameters of the inverse. That's a smooth. These have to be smooth functions, or to be more precise, analytic functions. So that's the demand which gives you a Lie group. Okay, so that's the formal part. We are not going to talk too much about Lie groups formally, simply because we don't have the time. But what we can always say is something like this, just by analogy with rotations. If you're first of all going to insist on one thing. There are many ways of parameterizing elements, but one choice you will always make, this is a choice you can always make, is that if you replace all the parameters by 0, or the 0 vector in your small r dimensional space, the origin always stands for the identity. So that's a demand you're going to make. Okay? Yeah? Now that you might say that's wrong because, or that doesn't work, at least in the example that we talked about. For S3, for example, we said this was, if we are using x plus iy, x minus iy, u plus iv, minus u plus iv, the alpha beta minus beta star alpha star notion. The identity, for this parameterization, the identity for SU2 became 1 0 0 0. That was the parameter space, not 0 0 0 0, right? However, can easily parameterize this by replacing x by 1 minus x, right? That is, you can write this as 1 plus x prime. This is 1 plus x prime, and use x prime y uv as your parameters, in which case x prime equals 0 will correspond to x equal to 0, x equal to 1, which means for the new parameterization, this point will be 0 0 0 0. Okay? Is that clear to everybody? That is, you can, the point I'm trying to make, this is of course just an example. The point I'm trying to make is you can always reparameterize and insist that the identity is given by 0 parameters. Okay? So if you are going to talk about a parameterization which is 0 plus a very small value, this is going to be a result which is close to the identity. Okay? And now we get into a bit of a problem, because what do you mean when you say it's close to the identity? After all, closeness, do we have a notion of that? Are we talking about matrix space? The answer is we are really, but instead of going into the details of that, it's easier for us, perhaps, to think about this if we just go into talking about the representations. Because in physics, we are only going to use the representations anyway. Why is it easier for us to talk in terms of the representations? Yes?
It has a corresponding basis vectors in the
Yeah, but
space.
okay,
We
the
can act
important
the
thing is the representations are ultimately linear operators or matrices. They have a vector space of their own where you can easily impose a matrix structure. So while you cannot, for group elements, you cannot say that this result is identity plus some small correction, right? Because what does it mean to say some small correction? What does it mean to say group element is small? Or what does it mean to say you're adding a group element to another? This, of course, becomes clumsy, and it becomes very difficult to sustain this. But what you can always say is if you take a representation, DG0 must be the identity where, I mean, okay, I'm going to talk about the matrix representation simply because it helps fix my language. So if I am talking of a n-dimensional matrix representation, this is an n by n. This is going to be an n by n identity matrix, and then you can easily say if epsilon bar is a small vector, some matrices, some n by n matrices, right? Of course, plus higher order terms. Okay. All I'm saying is that now the plus makes perfect sense. These are matrices. You can add them together, and you can say that okay, if you have parameter 0, you get identity. If you have parameters epsilon 1, epsilon 2, epsilon 3, epsilon 4, and they are all very small, then you get epsilon 1 times the matrix plus epsilon 2 times the matrix plus epsilon 3 times the matrix, and so on. Plus, of course, higher order terms. To linear order, this is what you're going to get. This is okay. This is nothing but a Taylor expansion. That's all you're doing. You're saying that this connection between the parameters on the one hand and the matrices on the other is a smooth connection. That's what being a Lie group guarantees us. And then all you are saying is you can expand the matrix out about the identity in a Taylor series, and this is just the first order term of the Taylor series. So what physicists always do is they throw in a I here. Mathematicians often don't. So if you're reading a mathematics book on Lie group versus Lie algebra and a physics book, you may very often be thrown by some strange signs which a mathematician's book may have. Or a mathematician would be considering our signs strange, I guess. But can you tell me why a physicist puts in an I? And mathematicians sometimes do, but most mathematicians don't. Why is that? Why would you like an I?
Unitarity.
Yeah, basically because in physics we often are looking for unitary representations or unitary matrix representations. And if this matrix is unitary, then the ANs turn out to be Hermitian. Okay. By the way, it's not really unitarity which makes the physicist choose the I. It's really the Hermitianity, because even a mathematician will often deal with unitary representations. Not a problem. Okay. However, to a mathematician, there's something very special about Hermitian matrices. A mathematician would say, okay, if you don't have the I here, what you have are anti-Hermitian matrices. But fine, anti-Hermitian matrices are fine. Why don't you work with them? In physics, we would love these matrices to actually talk about physical observables, especially in the quantum mechanical context. And their Hermitian matrices or the corresponding Hermitian operators are things which we like. Okay. So the I really is not so much for the unitarity. That is common to both mathematicians and physicists. The I is really to make these things Hermitian. Okay. And so if you don't put in the I, chances are there will be, especially in the commutation relations, you will see some strange factors coming in, especially strange minus ones, etc. coming in. Strange simply to us, because we are used to certain commutation relations. The SU2 commutation relation may end up looking very different to us if we get to open just an arbitrary mathematics book. Okay? So this is where the connection between Lie groups and Lie algebra starts coming in. What you see is this, that if you are very close to the identity, you will get operators or matrices depending on which representation you're using. One for each, so each parameter, and these are going to be my generators. And the next step is going to be to show that all that you really need to worry about in talking about the connection, about this connection, at least almost all, are these quantities, the commutators of these operators. And then we go on to talk, then we abandon Lie groups for the time being and talk about Lie algebras. So this connection is what we are going to start with on the next day. That is, how is it that the commutator becomes so important? We have already seen that. By the way, that's why I also insist that you take a look at the at my rotation videos, simply because this connection is already there in the rotation videos in a special case, and knowing them in a special situation actually makes it easier to understand the more general and hence more complicated connection. The important point is, ultimately, knowing the commutators is enough to know the entire structure of the group, or almost enough to know the entire structure of the group. So instead of worrying too much about the full D group, which is more complicated, and which has, which is more complicated simply because the composition rules between the functions could be very, very complicated. That is, the composition rules between the parameters. Here, on the other hand, you're dealing with operators whose or matrices whose commutator is all you really have to worry about. This is way, way simple. So Lie algebras gives us a very simple way of looking into Lie groups and talking about their properties easily. So this is what we are going to do next Tuesday. But in the meantime, I would insist that you take a look at the rotation videos, simply because that will make following the general thing a lot easier. Okay, so I will call it a day today. We'll start with the Lie algebra proper the next day. Any questions?
Sir, if we